Hey there, my friend. Tonight, we're going to slow everything down and gently explore the hidden force that shapes your world and every world: electricity. You don't need to understand it all. Just listen, relax, and let the current of thought carry you deeper into sleep. Let's begin. Chapter 1. What is electricity, really? Electricity is one of the most fundamental forces in the universe, yet it remains surprisingly misunderstood. When most people think of electricity, they imagine the flick of a light switch, the glow of a computer screen, or the crackling bolt of lightning tearing through the sky. But these are just surface expressions of a far deeper phenomenon, one rooted in the very fabric of matter itself. At its core, electricity is about charge, a property carried by certain particles, most notably electrons and protons. Charge is not a substance or a material. It is a fundamental attribute, much like mass. It defines how particles interact through one of nature's four fundamental forces: the electromagnetic force. This force is responsible not just for what we call electricity, but also for magnetism, light, chemistry, and nearly every interaction between atoms and molecules. The universe is filled with charged particles, and where there is charge, there is electrical interaction. Opposite charges attract, like charges repel. This basic rule gives rise to incredibly complex systems. Inside an atom, negatively charged electrons are bound to positively charged protons in the nucleus through electrical attraction. Without this force, atoms wouldn't exist. Without atoms, matter wouldn't exist. You wouldn't exist. Electricity, as we experience it, however, emerges from the motion of these charged particles. In materials like copper, silver, or gold, known as conductors, some electrons are not tightly bound to any single atom. They can move freely through the material, creating what we call an electric current. But this current is not a torrent of particles flying like bullets down a wire. In fact, the drift speed of electrons in a wire carrying household current is incredibly slow, just millimeters per second. The real movement of electricity is not the mass of the particles, but the signal, the electric field that pushes the electrons. That field moves nearly at the speed of light. To better understand this, imagine a long, narrow pipe filled with marbles. If you push one marble in from one end, another marble immediately pops out from the other. The marbles themselves have barely moved, but the push, the disturbance, traveled instantly through the chain. This is similar to how electric fields push electrons. The electrons move sluggishly, but the field, the influence, propagates almost instantly. This is why flipping a switch lights up a bulb across the room instantly, even though the electrons themselves aren't rushing there in a straight line. But electricity doesn't require wires to exist. It can exist in open space, inside your body, or within clouds before a storm. It arises wherever there are charges and where those charges move or change in position. When they do, they create an electric field, a region around them where other charges feel a force. The strength of that field depends on the amount of charge and the distance from it. It's invisible, but it shapes how particles interact, move, and combine. It's an unseen structure in space, not made of particles, but of influence. The idea that something invisible could exert real force, shape real outcomes, and dictate real movement was once radical. Today, it is fundamental. That force, what pushes charges to move, is called electric potential, often referred to as voltage. Voltage is not a force itself, but a kind of electrical pressure that causes charges to flow. When you connect a battery to a circuit, the battery establishes a difference in potential between 2 points. The electric field generated by this difference causes free electrons in the wire to drift toward the region of higher potential energy, releasing their energy along the way as light, heat, or motion. In many systems, it's not just the presence of charge that matters, but its arrangement. Charges can build up and remain in place, as with static electricity. When you rub a balloon on your hair, electrons transfer from one surface to another, creating an imbalance of charge. These excess charges remain until they find a path to neutralize, sometimes discharging in a tiny spark, a miniature lightning bolt. Static electricity is a useful reminder that electricity is not always about movement. Sometimes it is stored, sometimes it waits. This idea of storing electricity leads us to capacitors, devices that hold electric charge in separated layers. A capacitor consists of two conductive plates separated by an insulator. When a voltage is applied, electrons accumulate on one plate, creating a strong electric field across the insulator. The stored energy can then be released later. Capacitors are crucial for smoothing power in circuits, powering flash photography, and even tuning radio frequencies. They are silent, invisible containers of potential, ready to release stored energy in the blink of an eye. Underlying all of this is the principle of charge conservation, the idea that electric charge can neither be created nor destroyed. In every interaction, the total amount of charge remains constant. This symmetry is fundamental to our understanding of the universe, much like conservation of energy or momentum. If a particle with positive charge appears, it must be accompanied by another with equal negative charge. Charge is not just a curious property. It is a deeply embedded feature of nature, balanced and enduring. The rules that govern electricity were first hinted at centuries ago, but they were formalized into mathematical laws only in the 19th century. Scientists like Charles-Augustin de Coulomb, André-Marie Ampère, and James Clerk Maxwell created the foundation that describes how charges behave and how fields propagate. These laws are still used today, not only in electronics, but in space science, biology, and even quantum field theory. Electricity also underlies how your own body works. Nerve cells communicate using tiny electrical impulses. When a signal travels along a nerve, it is not a chemical cascade alone, but a wave of depolarization, an electrical signal caused by ions flowing in and out of the nerve membrane. Every time you think, move, or feel, electricity is involved. Your brain is an incredibly complex web of bioelectrical patterns, constantly shifting and reforming in a silent, continuous dance. When your heart beats, it is because of an electrical impulse triggering muscle contractions in precise rhythm. When those rhythms fail, a shock of electricity can sometimes bring them back. Not because the shock is magic, but because the body is an electrical system. Electricity also plays a role on planetary and cosmic scales. The Earth itself has a weak but significant electric field, and its atmosphere is home to a global circuit that involves thunderstorms, the ionosphere, and the Earth's surface. Cosmic rays, high-energy particles from deep space, ionize particles in our atmosphere and contribute to this field. This quiet electrical activity surrounds us constantly, unnoticed, yet always present. On a deeper level, electricity is linked with some of the most mysterious aspects of modern physics. In quantum electrodynamics, the quantum theory of how light and matter interact, electricity is mediated by particles called photons. These are the force carriers of the electromagnetic interaction. Every push, pull, spark, or wave involves the exchange of photons. In this view, what we think of as a field is not a smooth surface, but a sea of quantum fluctuations, where interactions occur through the probabilistic exchange of these quantum messengers. Even more fundamentally, the vacuum of space, what we often think of as nothing, is not empty. It is a turbulent field, filled with virtual particles constantly popping in and out of existence. These fluctuations have electric charge, however fleeting, and contribute to what we call the vacuum energy. Electricity is not confined to wires and circuits. It is an integral part of the structure of reality. Still, for all its clarity in equations and experiments, electricity resists full intuition. We can see its effects, measure its flow, and use it to build complex machines, but we cannot see the field itself. We cannot touch a charge. We cannot isolate a spark in a jar without it leaping away the moment it finds a better path. It is everywhere and nowhere, hidden behind the familiar, powering everything we rely on, and yet fundamentally invisible. You could argue that electricity is not a thing at all, but a relationship. It is a way that nature communicates motion between particles, a language of interaction, not substance. It is both what binds atoms and what makes machines. It is embedded in matter and in space. If gravity holds the large-scale universe together, electricity holds the small-scale world in place. And even now, we don't fully understand where charge comes from. We can describe it, predict it, work with it, but we can't explain why electrons carry exactly the same amount of negative charge or why protons have the exact opposite. It's simply a property that exists, a number with no deeper origin known to us. And that's where the mystery begins. In a way, electricity is like a whisper from the universe, a soft instruction embedded in every atom, every cell, every star. It asks for nothing but attention. It offers no color, no shape, no sound. And yet, from it comes light, life, motion, and thought. It is the quiet breath of the cosmos, flowing through copper wires, nerve fibers, thunderclouds, and quantum space. Always moving, always present, hidden, but never absent. And maybe that's what makes it beautiful, that something so essential could remain so invisible. That the force that powers our cities and our thoughts could also be the quiet current that threads the stars. Chapter 2. The Flow That Never Ends. How Current Moves. When we speak about electricity in everyday terms, we often imagine something moving, a flow of energy through wires, a current lighting up a room or powering a device. But what exactly is flowing, and how does this invisible river make its way from point to point without losing itself in the process? The answer lies in the concept of electric current, a deeply physical process rooted in the microscopic world. Electric current is the flow of electric charge. In most cases, that charge is carried by electrons, though in some systems, like salt water or plasma, other charged particles, both positive and negative, can also move. Still, in the circuits that power our homes, computers, and cities, it is electrons that do most of the work. Current, at its core, is defined by how much charge passes a given point over time. When we say a wire carries a current, we mean that a measurable number of electrons are drifting past each point in that wire every second. But the word drifting is important here. In metals, electrons are not bound to individual atoms. Instead, they move freely, like a gas of particles embedded in a rigid lattice of positively charged ions. This forms what physicists call a sea of electrons. In the absence of any electric field, the motion of these free electrons is random. They dart in all directions, constantly colliding with atoms and with each other. There's motion, a lot of it, but no preferred direction, and thus no net current. It is only when an electric field is applied, such as by connecting the ends of a conductor to a voltage source, that this chaos becomes biased. Electrons begin to favor one direction, ever so slightly, and that tiny statistical nudge is what gives rise to current. Surprisingly, the drift velocity of these electrons is extremely slow. In a typical copper wire carrying a few amps of current, the average electron drifts at mere fractions of a millimeter per second. This is much slower than the speed of light, slower even than the motion of a crawling insect. The electrons themselves are not racing through the wire in a dramatic surge. They are slowly nudging forward, bouncing along the way, driven by the ever-present field. And yet, when you flip a switch, the light turns on nearly instantly. This apparent contradiction is resolved when we consider that what propagates quickly is not the electrons, but the electric field, the instruction, not the messengers. The electrons in a wire are already in place, like beads on a string. When the field is applied, all the electrons begin to shift in response. One end of the wire receives a push, and that influence is communicated at nearly the speed of light throughout the conductor. It's as though the entire chain of electrons responds together, even though each individual only moves slightly. The signal travels fast. The matter does not. This behavior is somewhat analogous to water in a pipe. The individual molecules of water don't need to move from one end of the pipe to the other to create flow. When pressure is applied at one end, the whole column of water responds. Likewise, the electrons in a wire form a kind of fluid that responds collectively, even though the individuals move slowly and randomly. In some materials, this flow is smooth and unimpeded. These are the conductors, materials with many free electrons that can move easily in response to an electric field. Metals like copper, silver, and gold are among the best conductors, and their atomic structure allows electrons to flow with minimal resistance. However, even in these materials, collisions occur. Electrons still interact with the vibrating lattice of atoms, losing some of their energy as heat. This is why wires warm up under heavy current. The energy lost in collisions becomes thermal. There are also materials known as insulators, where electrons are tightly bound to their atoms and cannot move freely. In insulators like rubber, glass, or certain ceramics, there are no available energy states nearby for electrons to jump into, so current cannot flow under normal conditions. This makes insulators ideal for protecting and containing electric circuits. Between these extremes lie the semiconductors, materials whose conductivity can be adjusted by external conditions or internal structure. Silicon, the backbone of modern electronics, is a semiconductor. By adding tiny amounts of impurities, a process called doping, one can create materials that allow controlled flow of electrons, or even the movement of holes, the absence of electrons, as if they were positive charges themselves. Semiconductors allow us to build transistors, diodes, and integrated circuits, devices that shape and redirect current with extraordinary precision. Electric current comes in two major forms: direct current, DC, and alternating current, AC. In DC, electrons flow in a consistent direction. Batteries produce DC, supplying a steady stream of charge from one terminal to another. In contrast, AC reverses direction periodically. The current in household electrical systems oscillates back and forth, typically at 50 or 60 times per second, depending on the country. This alternating motion doesn't mean that electrons shuttle back and forth across the room. Rather, they vibrate slightly in place, moving back and forth within a tiny range. The energy, however, is transferred efficiently. AC has significant advantages for large-scale power distribution because it can be transformed, stepped up or down in voltage, using simple devices called transformers. This allows power to be transmitted over long distances with minimal loss and then reduced to safe levels for household use. On a deeper level, current is not just about the motion of particles. It also affects the space around it. A moving charge produces a magnetic field, and this is where electricity begins to blend into magnetism. A simple loop of current generates a magnetic field similar to that of a bar magnet. Larger currents, such as those in power lines or inside motors, can generate strong magnetic fields that interact with other currents or materials. This interplay forms the foundation of electromagnetism, a unified framework in which electric and magnetic fields are deeply intertwined. At the atomic level, current flow is influenced by quantum rules. Electrons in a conductor do not move individually like marbles. Instead, they follow the rules of quantum statistics. In a metal, electrons occupy a range of energy states, and only those near the top can respond to electric fields. Their motion is influenced not just by collisions, but by the underlying structure of quantum states available to them. This leads to phenomena like quantum tunneling, where electrons can pass through barriers that, classically, they should not be able to cross. A principle used in scanning tunneling microscopes and quantum computing. Current can also flow in unexpected ways. In a superconductor, for example, resistance drops to zero below a critical temperature. Electrons form paired states known as Cooper pairs, which move through the lattice without scattering. Once a current is established in a superconducting loop, it can circulate indefinitely without energy loss. This is not just efficient, it is fundamentally different from any behavior seen in classical conductors. Superconductivity challenges our intuition and demonstrates how quantum mechanics governs even macroscopic phenomena. Another curious aspect of current is that it doesn't always require a material medium. In a plasma, an ionized gas, both electrons and positive ions move freely, allowing current to flow in open space. This occurs in lightning bolts, fluorescent lights, and even in stars. The sun, for instance, is a vast sphere of plasma, its light and heat emerging from nuclear fusion, but its outer layers are governed by electric and magnetic interactions among charged particles. Even in the vacuum of space, current can move through vacuum tubes, devices that once powered early electronics. In these tubes, electrons are emitted from a heated filament and travel through vacuum toward an anode, guided by electric fields. This form of current does not require wires or solid material at all, only charge, field, and space. Ultimately, current is an emergent behavior. It arises from the collective motion of vast numbers of particles, yet it can be treated with simple, elegant laws. We quantify it in amperes, we regulate it with circuits, and we harness it to create everything from radio waves to computation. And while the electrons move slowly, the results appear fast, decisive, and powerful. Electric current never exists in isolation. It is always part of a larger cycle, a loop. For current to flow, there must be a complete path, a source of potential, a medium to carry the charge, and a destination. In this sense, current is inherently relational. It does not flow without cause. It does not appear without context. It is a response, a ripple in a sea of charge, compelled by potential and guided by the structure it inhabits. In all its forms, current reminds us that motion can be invisible, quiet, and even slow, and yet carry immense energy. That a barely perceptible drift of particles can light up cities, power machines, or carry thoughts along nerves. That speed is not always necessary for effect, that scale is not always visible, and that sometimes the most powerful flows are the ones we never feel. Perhaps there's something quietly profound about that. The world around you and inside you is filled with currents. In your walls, in your heart, in the sun, they flow without sound or color, shaping reality moment by moment. They require no praise and leave no trace, but their influence is everywhere. You may never see them, but they never stop moving. Chapter 3. Voltage, resistance, and the gentle push of energy. Electricity is not merely the movement of charges, but the consequence of an underlying imbalance. It begins with potential, with the quiet readiness of energy waiting to act. That potential is what we call voltage, concept as fundamental to electrical systems as pressure is to water. It is the gentle push that encourages electrons to move, the silent invitation that guides the flow of current from one point to another. Voltage is often described as electric potential difference. But what does that really mean? Just as a ball placed on a hill has potential energy due to its position, a charged particle in an electric field has the capacity to do work because of where it is relative to other charges. This difference in electric potential between 2 points, how much work a charge would do moving from one to the other, is what defines voltage. The greater the difference, the stronger the push. But unlike pressure, voltage does not depend on the movement of a substance. It's not a flow itself, but the potential for flow. To make this more tangible, imagine a battery. Inside, a chemical reaction creates an imbalance. One terminal accumulates excess electrons, while the other is left with a relative deficiency. This separation establishes a potential difference between the terminals. When a conductive path is provided, a wire, a filament, a circuit, the electrons are no longer trapped. The voltage pushes them through the circuit, allowing them to do work along the way. Lighting a bulb, turning a motor, or storing energy in another component. But the push is not forceful in the way we might imagine. It is constant, measured, and patient. Voltage is not consumed. It is not used up as current flows. Instead, it is the cause, the origin of the movement. Like gravity pulling an object downhill, voltage provides direction and encouragement, not the energy itself. The energy resides in the system as a whole, distributed between the source, the field, and the load. As charges move, they transfer energy from one part of the circuit to another, converting it into heat, light, or motion. But the journey is never without difficulty. Along every path, charges encounter resistance, the natural opposition to their movement. Resistance arises from the interactions between moving electrons and the atoms of the material through which they travel. These collisions cause the electrons to lose energy, which is then dissipated as heat. In conductors like copper or silver, the resistance is low, and electrons can travel with minimal disruption. In insulators like rubber or glass, resistance is so high that almost no current can flow at all. Resistance is not merely a nuisance, it is essential to how circuits work. It allows for control, for regulation. Without resistance, current would rush uncontrollably, limited only by the source's capacity. Components like resistors, semiconductors, or even the filaments in light bulbs make use of resistance to perform specific functions. When current encounters resistance, energy is transformed. It can be released as heat, like in an electric heater, or as light, as in the glowing filament of a lamp. The interplay between voltage, current, and resistance defines how electric energy behaves in almost every practical system. When voltage is applied to a circuit, current begins to flow. But how much flows depends entirely on the resistance encountered along the way. This balance is what determines how much power is delivered to each component and how efficiently a system operates. If resistance is too low, The current may become dangerously high, overheating wires and damaging equipment. If resistance is too high, the current may be too weak to power anything at all. This relationship is deeply consistent. It allows engineers to design circuits that behave in predictable ways. It also allows energy to be distributed across vast networks, from distant power stations to the smallest components in a microchip. The same principles govern both scales, from megawatts to milliwatts, from miles of transmission cable to microscopic traces etched on silicon. Resistance itself is not a fixed quantity. It depends on the material, yes, but also on temperature, length, and cross-sectional area. As a conductor heats up, its atoms vibrate more intensely, making it harder for electrons to pass without interference. This is why wires heat up under load, and why electrical systems must be designed to dissipate heat effectively. In some materials, particularly semiconductors, resistance can vary in response to voltage, light, or even the presence of magnetic fields. This variability allows for the creation of components that can act as switches, amplifiers, or memory, the foundation of digital technology. There are also materials that defy conventional resistance altogether. Superconductors, when cooled below a critical temperature, exhibit zero electrical resistance. In this state, current can flow indefinitely without any loss of energy. No collisions, no heat, no decay. Superconductivity is not only astonishing, it is still not fully understood. The quantum mechanical mechanisms that allow for such perfect flow challenge our understanding of materials and open the door to revolutionary applications, from magnetic levitation to lossless power grids. But even in ordinary materials, the subtle dance between voltage and resistance determines how energy moves. It defines the speed, the intensity, and the destination of every electron's journey. And although electrons themselves carry the charge, it is the field, shaped by voltage, that sets them in motion, like leaves carried by a current of air. In complex circuits, voltage is not just applied once. It is shaped, divided, redirected, and stored. Capacitors hold potential temporarily, releasing it when needed. Inductors resist sudden changes in current, smoothing transitions. Transistors act like valves, using small voltages to control larger currents. In all of these interactions, the gentle push of voltage encounters carefully chosen resistances, guiding the flow with precision and purpose. The human body, too, obeys these same principles. Nerve cells maintain voltage differences across their membranes, created by the distribution of ions. When a signal needs to travel, the voltage across the membrane shifts, allowing a current to flow briefly before resetting. This process, repeated millions of times per second across trillions of connections, forms the basis of thought, sensation, and movement. The same subtle interplay between push and resistance that powers machines also underlies every human experience. Voltage does not create current alone. It provides the conditions for current to exist. Without a complete circuit, without a path, the voltage cannot manifest its influence. Like pressure against a closed valve, it waits, silent but ready. Only when a connection is made does the flow begin, guided by the geometry of the circuit and the properties of the materials within it. Even in the absence of motion, voltage can exert a profound effect. It shapes the space around charges, creates tension in fields, and stores energy invisibly. Two metal plates separated by air can hold a voltage between them, storing energy without a single electron crossing the gap. This potential is real. It can do work, create force, and even cause breakdown in the medium if pushed too far. This is how capacitors function and how lightning forms. When voltage becomes strong enough, it overcomes the resistance of the insulating medium, air, and creates a sudden, violent current. The world is full of voltages, from the gentle resting potential of a living cell to the millions of volts building in thunderclouds. And while current is the actor, voltage is the motive, the reason, the purpose. It is the quiet desire of charges to move, to equalize, to find balance. That desire for balance is perhaps the most universal quality of electrical systems. Voltage arises from separation, from imbalance, and the system always seeks to restore equilibrium. Electrons move to neutralize charge differences, to bring order to disorder. In doing so, they create heat, light, and information. But at its heart, electricity is always a response to imbalance. Without that contrast, there is no force, no motion, no energy flow. The same is true, perhaps, in life itself. Without difference, there is no drive. Without separation, no purpose. Voltage is not loud. It does not announce itself with a spark or a hum. It exists quietly, patiently, waiting to act. It is stored in batteries, latent in clouds, dormant in circuits. And when the moment is right, it reaches out, not with chaos, but with order. Not with violence, but with quiet insistence. It is the gentle push behind every electrical action, from the flicker of a firefly to the power that hums through a city at night. Maybe it's fitting that voltage, the invisible force that starts everything, is never seen. It is the beginning of every current, the root of every light. It's not the movement, but the reason behind the movement. And in that quiet potential, in that stored difference, lies the possibility of everything that follows. Chapter 4. Your body, wired by nature. Electricity is not just the language of machines or the hidden power behind lightning storms. It is also a living language, one spoken in every cell of your body. From the flicker of a thought to the beat of a heart, electrical phenomena form the foundation of how life communicates, organizes, and sustains itself. While often unnoticed, this inner electricity is no less essential than the currents in a wire or the fields around a magnet. It is quite literally what keeps you alive. At the level of biology, electricity emerges from ions, charged particles like sodium, potassium, calcium, and chloride. Unlike the electrons that flow freely in metal wires, these ions are much larger and interact with complex biological structures, such as membranes, channels, and pumps. Cells are surrounded by a thin, selectively permeable membrane that regulates the passage of these ions. This membrane maintains a difference in charge between the inside and outside of the cell, creating what is known as a membrane potential. It is this subtle separation of charge that enables many of the body's most vital functions. The resting potential of a typical nerve cell is around 70 millivolts, meaning the inside of the cell is slightly more negative than the surrounding fluid. This voltage is not accidental. It is carefully maintained by proteins embedded in the cell membrane, including ion channels and pumps that move ions against their concentration gradients. These tiny molecular machines expend energy, often in the form of ATP, to create and preserve the imbalance. In doing so, they prepare the cell for action, for the transmission of electrical signals. When a nerve cell or neuron is activated, specialized channels open in the membrane, allowing sodium ions to rush in. This sudden influx causes the voltage across the membrane to rise, triggering a chain reaction along the length of the neuron. This traveling electrical signal, known as an action potential, is the basic unit of communication in the nervous system. Once it reaches the end of the neuron, it may trigger the release of neurotransmitters, chemicals that pass the message to another cell. But the signal itself, fast, precise, and unrelenting, is electrical in nature. This entire process, from resting potential to signal propagation and reset, occurs in just milliseconds, and it is repeated constantly, billions of times per second, across a vast network of neurons. The human brain contains roughly 86 billion neurons, each forming thousands of connections with others. This staggering complexity is orchestrated not by wires, but by electrochemical impulses moving with astonishing coordination. When you think, see, speak, or feel, you are experiencing the synchronized firing of countless action potentials, each one a delicate shift in voltage carried by moving ions. These signals do not exist in isolation. The electrical behavior of the brain generates measurable patterns, rhythmic oscillations known as brain waves. These waves, detected using techniques like EEG, electroencephalography, reveal how different regions of the brain interact. Slow delta waves dominate during deep sleep, while faster beta waves are associated with alert thinking. Though not electrical currents in the traditional sense, these oscillations arise from collective neuronal activity and reflect the ever-changing electrical landscape of consciousness. Elsewhere in the body, electricity plays a more mechanical role. The heart, a muscular pump working without rest, is governed by its own internal electrical system. Specialized cells in the sinoatrial node, often called the heart's natural pacemaker, generate rhythmic electrical impulses that spread through the heart muscle. These impulses cause the muscle fibers to contract in unison, producing the familiar heartbeat. Disruption in this electrical signaling can lead to irregular rhythms or arrhythmias, which may require medical intervention, sometimes in the form of a pacemaker that mimics the body's own electrical timing. Like neurons, heart cells rely on the movement of ions through channels and gates. Their ability to maintain and reset voltage differences across membranes ensures that each beat is followed by a period of recovery, preparing the heart for the next contraction. In this way, the heart is both a biological organ and an electrical circuit, governed by the same principles of potential, resistance, and timing that describe engineered systems. Beyond the brain and heart, electricity is involved in processes as diverse as muscle contraction, hormone release, and even cellular communication during embryonic development. Muscle cells, for example, respond to electrical impulses by releasing calcium ions, which in turn trigger the mechanical machinery of contraction. This process is carefully regulated to ensure coordinated movement, whether in the blink of an eye or the lift of an arm. In sensory systems, electricity enables the conversion of external stimuli into internal signals. When light strikes the retina, chemical changes in photoreceptor cells alter their membrane potential, initiating a cascade of electrical activity that travels through the optic nerve to the brain. Similarly, sound waves cause mechanical vibrations in the ear that ultimately generate electrical impulses interpreted as sound. In touch, temperature, taste, and smell, sensory neurons carry information as patterns of voltage changes. Electricity is not just present in the body, it is how the body interprets and responds to the world. Even at the single-cell level, electrical potential is a key part of life. Some unicellular organisms use voltage gradients to navigate their environments or to exchange signals with neighbors. In plants, slow electrical signaling regulates growth, response to injury, and interaction with the environment. The Venus flytrap, for instance, closes its trap using rapid changes in membrane potential, a dramatic example of plant bioelectricity in action. In the modern world, we can observe and manipulate these electrical properties in new ways. Techniques like transcranial magnetic stimulation and deep brain stimulation use electromagnetic fields to influence brain activity, often to treat disorders like depression or Parkinson's disease. Electrical signals recorded from the body can be interpreted by machines, a principle used in brain-computer interfaces and prosthetics that respond to neural commands. In these systems, the boundaries between biology and technology blur, connected by a common language: the movement of charge. Despite the complexity of these systems, the underlying physics remains the same. Voltage differences cause current flow. Resistance modulates that flow. Fields interact with matter. The same principles that govern circuits on a microchip also apply to your heartbeat, your thoughts, and your sensations. The elegance of this parallel is profound. Biology has adopted and refined the rules of electricity, evolving them into intricate systems that defy replication. Your body is not merely alive, it is electrically alive, and yet this intricate symphony is silent. You do not hear your neurons firing nor feel your ion channels opening. You do not notice the precise voltage shifts that power your brain's internal dialogue. But they are always there, always active. Even in sleep, your brain cycles through complex rhythms. Your heart maintains its rhythm. Your nerves stand ready to respond. The inner electricity never truly stops. This continuity, this ever-present movement of charge, suggests something deeper. That life itself is not static, but dynamic. That to be alive is not to hold a form, but to sustain a pattern of flow, a delicate balance between input and output, between energy stored and energy released. We are not objects, but systems. Not machines, but currents in flesh. When we speak of being wired, the metaphor is apt. Not because we are mechanical, but because we are networks. Networks of cells, of signals, of subtle voltage shifts that define sensation, memory, and identity. Your thoughts are not made of matter in the traditional sense. They are events shaped by the coordinated timing of electrical pulses moving through living tissue. And yet, for all its beauty, the system is fragile. Electrical signaling can be disrupted by trauma, toxins, or disease. The loss of balance in ion concentrations, the breakdown of membrane integrity, or the misfiring of neurons can have profound effects on health, behavior, and perception. The body's inner electricity must be constantly maintained, and when it fails, the consequences are immediate. Still, what is remarkable is not how often it breaks, but how reliably it works. For decades, perhaps even a century, your body maintains voltage gradients, moves ions, fires neurons, and contracts muscles without conscious effort. It adapts, repairs, learns. It is not just electrically active, it is electrically intelligent. Perhaps this is what makes our inner electricity so awe-inspiring. It is not imposed from the outside. It is not created by machines. It arises from within, from the interactions of molecules, cells, and tissues evolved to work together. It is embedded in the structure of life, inseparable from thought and sensation. And though it is invisible, it defines who you are, not just what you do, but what you feel, remember, and become. There is something quietly humbling in that thought, that you, in all your complexity, are a temporary alignment of moving charges, that every moment of awareness, every flicker of memory or emotion is carried by pulses of electricity flowing through a living circuit. You are not merely powered by electricity, you are written in it. Chapter 5. Electricity in Nature, from Lightning to Life. Electricity is often thought of as a human-made phenomenon, a product of wires, switches, and machines. But in truth, electricity was here long before us. It exists independently of our devices, embedded in the natural world. Before it powered homes, it powered the sky. Before it was harvested, It shaped the structure of matter and guided the evolution of life. The earth hums with quiet electric rhythms, and the universe is threaded with invisible currents that stretch across time and space. One of the most striking natural displays of electricity is lightning, an immense and sudden discharge of electrical energy from the atmosphere to the ground, or within the clouds themselves. Though familiar, lightning remains a complex phenomenon. It begins in the upper reaches of thunderclouds, where rising warm air causes collisions between ice particles, water droplets, and dust. These collisions separate charges, creating regions of positive and negative electrical potential. Typically, the upper part of the cloud becomes positively charged, while the lower part becomes negatively charged. As the difference in potential grows, an electric field forms. When this field becomes strong enough to overcome the insulating properties of air, it causes a sudden rearrangement of charges, a discharge. This is lightning, a narrow, high-temperature plasma channel carrying tens of thousands of amperes. It heats the surrounding air to temperatures hotter than the surface of the sun, causing it to expand explosively and create the sound we know as thunder. But lightning is not just a dramatic spectacle. It is part of a global electrical system known as the Earth's global electric circuit. This system connects the ionosphere, a region of the upper atmosphere ionized by solar radiation, to the Earth's surface. Thunderstorms act as generators in this circuit, pumping positive charge upward and negative charge downward. In fair weather, there is a constant, gentle flow of electric current between the ground and the ionosphere, sustained by this global balance. At any moment, thousands of thunderstorms are active around the planet, maintaining the electric tension between Earth and sky. This constant vertical current, though small, is always present. Even on a clear day, a sensitive voltmeter placed vertically in the air can detect the atmospheric electric field, typically around 100 volts per meter near the surface. This field can be influenced by local weather, pollution, altitude, and even cosmic events like solar storms. It's a subtle but ever-present reminder that our planet is not electrically neutral. It is dynamically charged. Electricity is not limited to the air. It flows underground as well. Telluric currents, or earth currents, are natural electric currents that flow through the Earth's crust. These can be induced by geomagnetic activity, changes in Earth's magnetic field caused by solar wind interacting with the magnetosphere. During geomagnetic storms, these currents can become powerful enough to interfere with power grids and pipelines, causing voltage surges and even damage to transformers. These subterranean currents reveal a truth we rarely consider. Even the ground beneath our feet is part of a dynamic electrical system. In the oceans, electrical activity plays a role too. Salt water is a natural conductor, and ocean currents moving through Earth's magnetic field generate electric fields through a process known as electromagnetic induction. In some marine organisms, these fields are detectable and useful. Animals like sharks and rays possess specialized electroreceptors, the ampullae of Lorenzini, that allow them to sense minute electrical fields generated by the movement of prey or by Earth's magnetic field itself. This ability, called electroreception, offers a silent, precise way to navigate and hunt in murky waters. Electricity also manifests biologically not only in humans, but across the entire spectrum of life. Certain fish, like electric eels, can generate their own electric fields using specialized organs made of modified muscle cells called electrocytes. These cells can be arranged in stacks, and when activated in unison, they create significant voltages, in some cases over 600 volts. These discharges are used for communication, navigation, defense, and hunting. But not all bioelectric fields are violent or visible. Many animals, including amphibians, birds, and mammals, generate weak electric fields as part of their physiology. These fields can influence cellular processes, guide healing, and possibly assist in internal navigation. Birds, for example, are believed to use a combination of magnetic and electric sensing to migrate across vast distances with incredible accuracy. In their eyes, certain proteins may act as quantum compasses, responding to changes in the Earth's electromagnetic environment. On the molecular level, electricity is involved in how cells maintain their internal environment, transmit signals, and interact with their surroundings. Every living cell has a resting membrane potential, a voltage across its membrane created by differences in ion concentration inside and outside the cell. This voltage is essential not only in nerve and muscle function, but also in more basic life processes like cell division and growth. Even in single-celled organisms, changes in membrane potential can trigger important behaviors, a kind of primitive electrical awareness. Some scientists propose that bioelectric fields play a role in developmental biology, the process by which embryos grow and take shape. During early development, gradients of voltage across tissues may influence how cells differentiate, migrate, and organize. This idea, sometimes referred to as bioelectric patterning, suggests that electrical fields could be a kind of blueprint, a silent architect guiding the formation of limbs, organs, and neural networks. Although still a developing field, it adds to the growing recognition that electricity is not just a feature of life. It may help shape life itself. Natural electricity can also emerge from the Earth's own geological processes. Prior to earthquakes, researchers have observed strange electrical and electromagnetic phenomena. Unexplained pulses, glowing clouds, and sudden spikes in telluric currents. These signals are difficult to study and even harder to predict, but they hint at a complex relationship between mechanical stress in rocks and the release of electrical charge. Some minerals, like quartz, exhibit piezoelectric properties, meaning they generate electric charge when compressed. Deep within fault lines, the buildup of stress could create subtle electrical precursors to seismic events, though no definitive early warning system has yet emerged. Beyond Earth, electricity is common in the broader universe. The solar system itself is a dynamic electromagnetic environment. The solar wind, a stream of charged particles emitted by the sun, carries electric and magnetic fields across interplanetary space. These fields interact with planetary magnetospheres, giving rise to phenomena like the auroras. On Earth, the aurora borealis and aurora australis appear when energetic particles from the solar wind spiral along magnetic field lines and collide with atoms in the upper atmosphere. These collisions excite the atoms, causing them to emit light in shimmering curtains of green, red, and violet. It is an ethereal display of solar electricity dancing through Earth's magnetic veil. Even in the depths of interstellar space, electricity leaves its mark. Plasma, a state of matter consisting of charged particles, is the most common form of visible matter in the universe. In plasmas, electric currents and magnetic fields govern behavior on cosmic scales. Filaments of plasma stretch across galaxies, influenced by electromagnetic forces that are far stronger than gravity on small scales. Stars themselves are electric phenomena, sustained by nuclear fusion, but structured and shaped by electromagnetic interactions in their outer layers. From the largest scales to the smallest, electricity is an organizing principle. It shapes weather and climate, guides evolution, sculpts landscapes, and flows through every living being. Unlike light, it does not need to be seen to be real. Unlike sound, it does not need to be heard to be felt. It is a silent architect of patterns, motion, and change. And yet, for all its presence, electricity is not always predictable. It flickers and dances, builds quietly, then releases with sudden force. It can heal and destroy, signal and confuse. Nature does not wield electricity with the precision of a circuit diagram. It moves chaotically, in pulses and storms, in rhythms that blend physics and complexity. Perhaps that is what makes electricity in nature so captivating. It reminds us that the universe is alive with movement. Not just motion through space, but motion through potential, through tension and release. It reminds us that nature does not wait for permission to act. It builds until the moment is right, and then, with a flash, it changes everything. You, too, are part of this pattern. The electrical fields that rise in your cells are not separate from those in the sky. They obey the same laws, follow the same forces. In a very real sense, the lightning above and the spark of thought within you are different expressions of the same invisible current, flowing, organizing, illuminating, not separate, just differently scaled. Chapter 6. The invisible field around you. Stand still for a moment, and though you may not feel it, you are immersed in something invisible, something that quietly, relentlessly exerts its influence on everything around you. It does not make a sound. It has no scent, no color, and yet it reaches across space and interacts with matter at every scale. This unseen presence is the electric field, one of the fundamental ways in which the universe communicates force. An electric field is not a thing in the usual sense. It is not a stream of particles or a flow of material. Rather, it is a condition of space itself, a property of the environment that is shaped by the presence of electric charge. Where there is charge, there is an electric field. And where there is an electric field, other charges will feel a force. This interaction defines much of what we observe as electrical behavior. From the subtle workings of atoms to the operation of massive power systems. The concept of a field was once radical. Before it, physicists understood forces as something exerted directly by one object upon another, a kind of instantaneous action across a distance. But this view became unsatisfying, particularly for electricity. If two charges affect each other from across space, how is the interaction transmitted? What mechanism allows one to know the other is there? The answer, introduced gradually through the work of thinkers like Michael Faraday and James Clerk Maxwell, was the field. Rather than charges interacting directly, each charge alters the space around it, creating a field that extends outward in all directions. Any other charge placed within that field experiences a force, not because the first charge reaches out and grabs it, but because the local space around it is already shaped. This idea reframes our understanding. A single electron is not just a tiny particle. It is the source of a vast, invisible field that stretches out in space indefinitely. Its presence modifies the geometry of force in its vicinity, and when many charges are present, their fields superimpose, adding together to create complex patterns of influence. The result is an electric landscape, a hidden structure that determines how forces arise and how motion occurs. The strength of an electric field depends on the amount of charge that generates it and the distance from that charge. Close to a single point charge, the field is strong and radial, pointing directly away from a positive charge or inward toward a negative one. As you move farther away, the field becomes weaker, fading in strength with distance, but never truly disappearing. In ideal conditions, it extends infinitely, though its effects eventually become indistinguishable from zero. Electric fields do not require continuous sources of charge to exist. Even temporary separations of charge, as occur in capacitors, clouds before a storm, or even in individual molecules, can generate fields. A dipole, formed by two opposite charges placed close together, creates a unique field pattern that is asymmetric, more complex than a single charge. These small-scale fields have consequences, influencing how molecules align, how surfaces interact, and how electromagnetic waves propagate. In materials, electric fields can exist internally, influencing behavior in subtle ways. In dielectrics, insulating materials that respond to electric fields, the field causes tiny shifts in the position of charges within atoms and molecules. These shifts don't create a flow of current, but they do produce polarization, a state in which positive and negative charges are slightly displaced. This internal rearrangement modifies the field itself, often weakening it or redirecting its path. This interaction is the basis for capacitors and many other components in electronic devices, where fields must be controlled precisely. Electric fields also play a vital role in chemical bonding and molecular structure. In atoms, the attraction between the negatively charged electrons and the positively charged nucleus is governed by the electric field. The shape of electron orbitals, the strength of chemical bonds, and the geometry of molecules are all determined by how electric fields shape the space around and between particles. It is this internal architecture, forged by fields, that allows chemistry to occur and life to emerge. But fields are not static. They change when charges move. A moving charge, a current, produces not only an electric field, but also a magnetic field. And when the electric field changes in time, it generates a magnetic field even in the absence of charge. This dynamic interplay is at the heart of electromagnetism. It is how light is produced. An accelerating charge emits changing electric and magnetic fields that propagate through space, electromagnetic waves, which include visible light, radio waves, and X-rays. These waves do not require a medium to travel through. The electric and magnetic fields sustain each other, forming a self-perpetuating pattern that moves outward from the source at the speed of light. This realization, that changing fields give rise to one another, was a milestone in physics. It unified electricity and magnetism into a single theory, electromagnetism, described mathematically by Maxwell's equations. These equations reveal that the field is not just a bookkeeping tool or a metaphor for force. It is the physical entity through which energy moves and interactions occur. The implications of this are profound. In modern physics, the field is no longer merely a convenience. It is the foundation of reality. The quantum field theory that underpins particle physics describes every particle not as an isolated object, but as a localized excitation of an underlying field. Electrons, photons, quarks, all are understood as disturbances in their respective quantum fields, interacting through the exchange of other quanta, such as virtual photons in the case of electromagnetism. This framework means that electric fields are not abstractions. They are expressions of real, physical properties of space. Even in a vacuum, where no particles are present, fields remain. They can fluctuate, interact, and produce measurable effects. One such effect is the Casimir force, in which two uncharged metal plates placed very close together experience an attractive force due to alterations in the quantum electromagnetic field between them. These phenomena suggest that empty space is not truly empty. It is alive with potential, structured by invisible fields that can affect matter and energy. On Earth, the electric field is not just a laboratory curiosity. It shapes natural phenomena in surprising ways. The field between the ground and the ionosphere, part of the Earth's global electric circuit, influences how particles move in the atmosphere. It affects cloud formation, particle aggregation, and even biological systems. Some organisms, like bees, appear to sense electric fields and use them to detect flowers. Spiders may use the field as a navigational aid when ballooning on silk threads. These are not theoretical curiosities. They are real, observable interactions between life and the unseen structure of space. Even in your immediate environment, electric fields are present and active. The devices around you, phones, chargers, screens, all produce local fields. High-voltage power lines emit measurable electric fields, which can influence nearby conductors and, at high intensities, even ionize air. Your body itself both senses and generates electric fields. The subtle voltages across cell membranes create small but measurable fields, and the coordinated activity of neurons produces complex patterns detectable by instruments. These fields do not leave your body, but they do extend outward, faint traces of the internal electrical activity that sustains your thoughts and movements. Electric fields do not make sound. They are not felt in the same way as temperature or texture. But they are there, structuring the interactions of matter, guiding particles through circuits, and giving shape to the behavior of systems large and small. They are quiet architects, persistent and patient, working without notice. Perhaps what is most striking about electric fields is that they unify what we often think of as opposites: stillness and motion, emptiness and form. A single charge at rest creates a field that stretches forever. No movement is required. The mere presence of charge alters the space around it, and when charges move, they disturb the field, send waves outward, and communicate across space. In this view, all force is local, but all influence is global. Fields connect objects across distance, not by stretching between them, but by shaping the space they both inhabit. You live within a sea of these fields. You always have. They do not demand your attention, but they shape your world. Every structure, every bond, every interaction is filtered through this invisible medium. From the formation of molecules to the operation of neural circuits, from the flight of a photon to the arc of a lightning bolt, the electric field is there, unseen but never absent. And in some quiet way, perhaps that's a reflection of us too. Much of what matters is not what we can see or touch, but what we exert on the world simply by being present. The shape of our lives, our thoughts, our actions, our impressions, extend beyond us in ways that may not always be visible. Like fields, we influence what surrounds us, often without knowing. Chapter 7. Nikola Tesla and the Dream of Wireless Power. When we speak of electricity today, we often think in terms of systems, grids, outlets, circuits, batteries. Electricity has become so domesticated that its presence feels almost mundane. Yet at the turn of the 20th century, it was something closer to a miracle, raw, untamed, radiant. It was during this time that one man emerged with a vision so ambitious that even now, more than a century later, it remains both iconic and enigmatic. That man was Nikola Tesla. Tesla did not invent electricity, nor did he discover electromagnetic fields, but he reshaped how humanity interacted with them. His deep intuition for alternating current, his extraordinary demonstrations of high-voltage phenomena, and his dream of wireless power transmission transformed both the practical and imaginative landscape of modern science. While many of Tesla's designs were rooted in physics that remains valid today, others pushed the limits of theory, merging scientific insight with visionary speculation. At the heart of Tesla's dream was the idea that electrical energy could be transmitted wirelessly over long distances, not just for communication, but as a practical and universal form of power delivery. This idea was not merely about eliminating wires. It was about transforming the planet into a single electrical organism, a resonant structure through which energy could be shared freely and efficiently. To understand the foundation of this dream, we must first look at Tesla's profound contributions to alternating current, or AC. Unlike direct current, which flows steadily in one direction, AC oscillates, changing direction many times per second. This property allows it to be transmitted over long distances with less energy loss and transformed easily between voltage levels using simple coils. Tesla championed the AC system in opposition to Thomas Edison's preferred DC, and his success laid the foundation for modern power distribution. But for Tesla, AC was just the beginning. He saw in high-frequency alternating currents a doorway to new phenomena. Through his development of devices like the Tesla coil, a high-voltage resonant transformer, he was able to produce massive electrical discharges and electromagnetic fields without direct contact. His demonstrations, where arcs of electricity danced through the air and light bulbs glowed without wires, were not just theatrical. They illustrated the possibility that energy could be transmitted through space. Tesla's wireless power idea was not based on electromagnetic radiation alone, such as the radio waves used in modern communication. Instead, he believed that energy could be transmitted through the Earth itself, using it as a conducting medium, and through the atmosphere, by establishing standing waves that would resonate around the planet. In essence, Tesla envisioned the Earth as a giant electrical body, capable of being energized like a massive tuning fork. To explore this idea, Tesla began construction of the Wardenclyffe Tower in Shoreham, New York in the early 1900s. The tower was a towering wooden structure topped with a copper dome, designed to serve as the terminal for high-voltage, high-frequency oscillations. Beneath it, a deep grounding system was constructed to interact with the Earth's conductive layers. Tesla believed that by pumping electrical energy into the planet at its resonant frequency, he could set up global standing waves, fixed patterns of electromagnetic vibration that could be tapped into from anywhere in the world. This concept of Earth resonance is not entirely without precedent. In the mid-20th century, physicists confirmed the existence of the Schumann resonances, a set of natural frequencies at which electromagnetic waves resonate in the cavity formed between the Earth's surface and the ionosphere. These resonances, typically in the extremely low frequency ELF range, are real and measurable. However, the amount of power they can carry is minimal, and their frequencies are far lower than those Tesla envisioned. Tesla's theory was based on the belief that the Earth could support much higher frequency standing waves that could be driven by a sufficiently powerful oscillator, such as his tower. If successful, such waves might allow energy to be delivered across great distances without wires, as long as the receiver was properly tuned. He imagined towers across continents, each tapping into the Earth's oscillations, delivering power to homes, industries, and machines without physical infrastructure. It was a magnificent idea, but it was never completed. The Wardenclyffe project collapsed due to lack of funding. Tesla's backers, including J.P. Morgan, grew concerned when it became clear that Tesla intended not only to transmit information like Marconi's radio, but to give away energy freely, with no clear means of monetization. Without additional support, construction ceased. The tower was eventually dismantled, and Tesla's dream faded into legend. From a modern scientific perspective, Tesla's ideas were a mixture of brilliance and limitation. His understanding of resonance, high-voltage phenomena, and inductive coupling was profound. Many of his experimental observations remain valid and are still used in technologies like wireless charging and radio frequency systems. But the large-scale wireless transmission of power, especially through the Earth as a conductor, faces substantial theoretical and practical challenges. One issue is energy loss. The Earth is conductive, but not perfectly so. High-frequency currents tend to suffer from attenuation. They lose strength over distance, especially when the medium is irregular and layered, as the Earth's interior is. Atmospheric transmission over long distances is also subject to loss, interference, and scattering. While near-field wireless power systems, like inductive charging pads, work well at short range, their efficiency drops quickly with distance. Furthermore, the high voltages required to generate such large-scale waves pose serious safety concerns. Fields strong enough to deliver power across kilometers would create interference with sensitive electronics and biological tissues. Maintaining precise resonance conditions across varying environmental factors would be extremely complex. Despite these limitations, Tesla's ideas were not entirely wrong. In recent decades, scientists and engineers have revisited the principles behind wireless energy transfer, developing systems for resonant inductive coupling that allow for efficient, wireless charging of devices over short distances. Experiments with microwave and laser-based power transmission have shown that targeted energy beams can deliver power to drones, satellites, or remote sensors. And research into atmospheric electricity and Earth ionosphere interactions continues to advance our understanding of global electromagnetic behavior. Tesla's vision was grander than what physics currently allows, but not entirely disconnected from it. His genius lay not only in what he built, but in what he imagined. He did not see electricity as a tool to be controlled, but as a fundamental rhythm of nature to be harmonized with. For him, energy was not a commodity, but a language, a vibration that connected all things. Tesla's later ideas extended beyond wireless power into more speculative realms. He began to explore the notion that space itself might be filled with a subtle medium, what he referred to as the ether, through which energy could travel without resistance. While the concept of the ether was largely discarded following the advent of Einstein's special relativity, Tesla continued to believe in a form of interconnected energy space. In his view, the ether was not a material substance in the classical sense, but a dynamic background field that could support electrical vibrations, a place from which energy could be extracted and into which it could be returned. Interestingly, modern physics has in some ways circled back to similar-sounding concepts, though grounded in different theoretical frameworks. In quantum field theory, space is not truly empty but filled with fields that can fluctuate, interact, and give rise to particles. The idea of zero-point energy, the lowest possible energy that a quantum system can have, suggests that even a vacuum has measurable energy. While Tesla's notions of tapping into limitless ambient energy were ahead of their time and remain unproven, today's understanding of quantum vacuums and field energy offers a faint echo of the possibility that energy may yet be drawn from space itself, under the right conditions. In his later writings, Tesla often spoke of the universe as a system of waves, of energy, frequency, and resonance. One of his most often quoted lines, though of disputed origin, encapsulates his belief. If you want to find the secrets of the universe, Think in terms of energy, frequency, and vibration. Whether or not he ever said these words, they capture his worldview. For Tesla, to understand electricity was to understand nature itself. He died alone and nearly forgotten, his achievements overshadowed for a time by more commercially successful contemporaries. Yet today, his name is attached to everything from electric vehicles to scientific units, from pop culture icons to cutting-edge experiments. Tesla's legacy is not just in what he made, but in what he inspired. And perhaps that is the enduring value of his dream. Not in whether it worked exactly as he planned, but in the direction it pointed, toward a world where energy moves freely, where systems resonate with nature, and where technology is not imposed on the world, but drawn out from it. Maybe, in some quiet way, Tesla saw something we still do not fully grasp, that the universe is not merely mechanical, but vibrational, that power is not only what we generate, but what we tune into, and that the invisible forces around us are not barriers, but bridges, if only we learn to listen. Chapter 8. Electromagnetism, the unity of electricity and magnetism. For centuries, electricity and magnetism were studied as separate and distinct phenomena. One involved sparks, shocks, and the movement of charges. The other concerned mysterious attractive and repulsive forces around certain stones, needles that aligned with Earth's poles, and the invisible reach of iron. They seemed unrelated, one tied to lightning and electric currents, the other to lodestones and compasses. But as the 19th century unfolded, a profound realization emerged. Electricity and magnetism were not isolated forces. They were two aspects of the same deeper reality. This revelation did not happen all at once, but through a series of careful, interconnected discoveries. When scientists observed that electric currents could deflect magnetic needles, or that changing magnetic fields could induce electric currents, a pattern began to form. What was once seen as two domains of physics gradually merged into one unified framework, electromagnetism. At the heart of this unity lies a simple but powerful idea, that moving charges create magnetic fields, and changing magnetic fields create electric fields. The implications of this are vast. A wire carrying current generates a magnetic field around it, circling the wire in a predictable direction. This is not merely a property of the wire, but of the space itself. The act of moving charge reshapes the environment, imprinting a rotational structure into space, a magnetic field that did not exist before. Likewise, a magnetic field in motion can induce an electric field. This is the principle behind electromagnetic induction. When a magnet moves near a coil of wire, or when the magnetic field through a loop changes, a voltage is produced, driving current through the wire. It is not the magnet itself that causes the current, but the change in magnetic flux, the dynamic shift in the field over time. This relationship underlies the operation of electric generators, transformers, and the vast networks of power distribution we rely on daily. The culmination of these observations came in the form of four elegant mathematical expressions, now known as Maxwell's equations. James Clerk Maxwell, a Scottish physicist working in the mid-1800s, distilled the fragmented knowledge of electricity and magnetism into a unified theory. These equations described how electric fields arise from charges, how magnetic fields arise from currents, and crucially, how the two fields influence each other in time and space. One of Maxwell's most astonishing conclusions was that a changing electric field can generate a magnetic field even in the absence of any current. This meant that a self-sustaining wave of alternating electric and magnetic fields could travel through space, an electromagnetic wave. By solving his equations, Maxwell predicted the existence of such waves and calculated their speed. That speed, it turned out, was equal to the speed of light. This was not coincidence. It was revelation. Light in all its forms, visible, infrared, ultraviolet, radio, X-ray, is not separate from electricity and magnetism. It is their union in motion. A beam of light is a propagating disturbance in the electromagnetic field, with electric and magnetic components oscillating at right angles to each other and to the direction of travel. It requires no medium. It needs no wires. It is a pure expression of field interaction, born from the coupling of electricity and magnetism. In this way, electromagnetism links not only previously unrelated forces, but previously unrelated domains of science. Optics, once the study of light and vision, became a branch of electromagnetism. So did the study of circuits and the behavior of fields and materials. The implications extended far beyond physics labs. With this understanding came the birth of radio, the development of telecommunications, radar, television, and countless forms of wireless technology. Every transmission, every signal that travels through the air or across space owes its existence to this union. On a more foundational level, electromagnetism is responsible for the structure of matter. The atoms that make up the world are bound by the electric force between negatively charged electrons and positively charged nuclei. The arrangement of electrons around the nucleus and the way those arrangements interact with others gives rise to chemical bonding. The taste of food, the texture of fabric, the smell of rain, all of these are ultimately electromagnetic interactions between molecules and receptors. Even the solidity of matter is electromagnetic. When you press your hand against a surface, what prevents it from passing through is not some rigid barrier, but the repulsion between the negatively charged electrons in your hand and those in the surface. The atoms do not truly touch. They repel at microscopic distances due to overlapping electron clouds, regions of probability shaped by the electromagnetic field. You never actually touch anything in the strictest sense. What you feel is the interaction of fields. In the macroscopic world, electromagnetism governs electric motors, magnetic storage, induction heating, wireless charging, and countless other phenomena. In biological systems, it directs nerve impulses, heart rhythms, and muscle contraction. In space, it shapes the solar wind, controls the behavior of plasma, and bends the paths of charged particles in planetary magnetospheres. The auroras that shimmer across polar skies are not mere displays of color, but electric storms guided by Earth's magnetic field. Unlike gravity, which only attracts, electromagnetism is both attractive and repulsive. It can pull and it can push. This duality allows for balance, for structure, for the complexity of matter. Without electromagnetic repulsion, atoms would collapse. Without electromagnetic attraction, molecules would never form. The universe would be dark and still. In theoretical physics, electromagnetism holds a special place. It is the best understood of the four fundamental forces. Its behavior is described not only by Maxwell's classical equations, but also by quantum electrodynamics, or QED, the quantum field theory of electromagnetic interactions. QED predicts with extraordinary precision how particles like electrons and photons interact. It has been tested to accuracies better than 1 part in a billion. No other theory in science matches its predictive power. Yet even here, questions remain. Why does the electromagnetic force have the strength that it does? Why does the photon, the force carrier of electromagnetism, have no mass, allowing the force to reach across infinite distances? And why do charges come in such exact quantized values? These remain mysteries, embedded in the fabric of physical law. In some speculative frameworks, like those found in grand unified theories or string theory, electromagnetism is thought to have once been united with the other forces at high energies in the early universe. As the universe cooled after the Big Bang, these unified forces are believed to have separated through a process called symmetry breaking, giving rise to the distinct forces we observe today. If true, this would mean that electricity and magnetism, themselves a unity, are just one piece of a larger whole, the visible tip of a deeper structure waiting to be fully revealed. The unity of electricity and magnetism is not merely a scientific fact. It is a profound idea that different phenomena observed in isolation can be manifestations of a single underlying reality. What appears separate is often connected. What seems unrelated may only be different expressions of the same deeper pattern. This principle holds meaning beyond physics. In a world often fractured by categories, disciplines, and divisions, electromagnetism offers a quiet lesson that nature resists compartmentalization. The boundaries we draw are for our convenience. The universe does not recognize them. Perhaps this is the beauty of science, that it reveals unity where we once saw division, that it shows how sparks and magnets, circuits and light are not fragments, but parts of the same continuous field. That beneath the complexity of appearances lies a deeper coherence, always there, waiting to be seen. And perhaps, in some quiet way, that coherence extends to us as well. That we too are shaped by invisible forces, guided, connected, influenced by patterns we do not always see but are never truly apart from. Chapter 9. The Electric Universe, From Stars to Empty Space. When we look up into the night sky, we often imagine a universe ruled by gravity, vast celestial bodies tugging on one another, stars holding planets in orbit, galaxies swirling like eddies in a river of mass. Gravity dominates our intuitive understanding of space. It shapes the trajectories of planets and the expansion of the cosmos. Yet quietly and often invisibly, another force weaves itself through this cosmic structure, the electromagnetic force. Although far weaker than gravity at large scales, electromagnetism is the dominant force in environments where charged particles are abundant, and in much of the visible universe, they are. Plasma, a state of matter in which atoms are ionized and electrons move freely, is the most common form of matter in the cosmos. Found in stars, nebulae, stellar winds, and intergalactic space, plasma is not neutral. It responds to electric and magnetic fields, and in turn, generates them. Wherever plasma moves, electricity follows. On Earth, we encounter plasma in limited settings: fluorescent lights, lightning, auroras, or controlled environments like fusion research facilities. But in space, plasma is the default. The sun, for instance, is a sphere of roiling plasma. Its surface and corona teem with magnetic activity, loops, flares, and storms generated by the motion of charged particles in magnetic fields. These structures are not merely decorative. They are electrically driven phenomena that govern how the sun interacts with the solar system. The sun does not simply emit light. It streams charged particles outward in a continuous flow known as the solar wind. This wind consists mostly of electrons and protons traveling at speeds of hundreds of kilometers per second. It carries with it magnetic fields rooted in the solar corona, stretching across space and interacting with every planet it touches. These interactions give rise to phenomena such as magnetospheres, bow shocks, and plasma tails, invisible but measurable electrical features that shape the space around worlds. Earth's own magnetosphere created by electric currents deep within its molten outer core, acts as a shield against the solar wind. When the solar wind encounters this magnetic barrier, it is deflected and redirected, but not entirely stopped. Some particles spiral along magnetic field lines toward the poles, colliding with atoms in the upper atmosphere and creating the auroras, glowing curtains of ionized gases, shimmering in green and red. These auroras are electrical events, powered by the energy carried in the wind of our star. This interaction between stars and surrounding plasma is not limited to our solar system. In other stellar systems, particularly around young stars, magnetic fields can funnel material from surrounding disks onto the star's surface, causing powerful bursts of radiation. In highly magnetized stars, such as magnetars, electromagnetic activity becomes even more extreme. These neutron stars have magnetic fields trillions of times stronger than Earth's, strong enough to deform atomic structures and release sudden flares of energy that can be detected across the galaxy. On even larger scales, entire galaxies interact with interstellar and intergalactic plasma. Galactic rotation, the collapse of gas clouds, the motion of cosmic jets, all of these are affected by electromagnetic forces when the medium becomes ionized. The centers of active galaxies, for example, often host supermassive black holes surrounded by accretion disks of plasma. As material spirals inward, it is heated by friction and electromagnetic turbulence, producing intense radiation and magnetic fields. Some of this energy is channeled into collimated jets, narrow streams of plasma launched at near-light speeds far into intergalactic space. These jets can extend over hundreds of thousands of light years, visible in radio and X-ray wavelengths. They are not gravitational beams. They are electric and magnetic structures, controlled by fields, not mass. The study of astrophysical plasmas, the plasma behavior in stars, nebulae, and galaxies, is now a major branch of astronomy. Scientists use magnetohydrodynamics, MHD, to model how magnetic fields and flowing charged particles interact on vast scales. These models help explain how stars evolve, how magnetic fields influence star formation, and how energy moves through the cosmos. Observatories that study electromagnetic radiation across the spectrum, from radio waves to gamma rays, are, in a sense, measuring the electrical heartbeat of the universe. Still, not all aspects of the universe's electric activity are fully understood. Some researchers have proposed that certain large-scale cosmic phenomena might be better explained with electric currents and plasma dynamics playing a central role. These ideas fall under what has sometimes been called the electric universe hypothesis, a loosely defined set of alternative cosmological models that suggest electric and magnetic forces play a more significant role in shaping galaxies, structures, and even cosmic evolution than is recognized in standard models. While the term electric universe has captured public imagination, it's important to distinguish between mainstream plasma astrophysics, which is a well-established and mathematically rigorous field, and more speculative or fringe interpretations. In established astrophysics, electromagnetism is already central to many phenomena. But the standard model of cosmology, which includes dark matter, dark energy, and cosmic inflation, remains overwhelmingly supported by evidence from the cosmic microwave background, large-scale structure, and general relativity. That said, it is undeniable that electromagnetism plays a far greater role in shaping the behavior of matter at every scale than many non-specialists assume. It is not just a terrestrial force. It sculpts stars, shapes radiation belts, governs cosmic jets, and defines the energetic structure of nebulae. It gives rise to the radiation we detect across the universe, not just visible light, but the entire electromagnetic spectrum. In interstellar clouds, for example, magnetic fields can slow or accelerate the collapse of gas, influencing how stars form. In regions of starburst galaxies, the intense feedback from supernovae and stellar winds creates bubbles of plasma that expand outward, altering the intergalactic medium. These magnetic structures can span thousands of light years, invisible in optical light, but detectable in polarized radio emissions. Even in the tenuous vacuum of space, electricity leaves its mark. Cosmic rays, high-energy charged particles, some accelerated by supernova remnants or galactic nuclei, zip through the universe at nearly the speed of light, interacting with magnetic fields and losing energy through electromagnetic processes. Their origins, pathways, and interactions all depend on the electric and magnetic conditions of the interstellar medium. As space-based observatories become more sensitive, we continue to uncover layers of electromagnetic complexity woven through the cosmos. Satellites like the Parker Solar Probe and the Solar Orbiter are studying the sun's magnetic fields and particle emissions in unprecedented detail. Meanwhile, telescopes operating at long wavelengths, such as LOFAR or the Square Kilometer Array, are mapping the faint radio signals that trace cosmic magnetism across billions of years. And still, beyond all this observable structure lies the quantum layer, where the quantum vacuum itself is never at rest. Even the emptiest regions of space seethe with virtual particles, fluctuations in the electromagnetic field that briefly emerge and vanish. The very idea that there is such a thing as empty space has been replaced by a deeper understanding that space is not inert. It has properties, structure, and energy. It can bend, ripple, and resonate, and it is filled always with the silent presence of fields. Electricity, then, is not a human invention. It is a universal language, spoken across void and star alike. Its currents flow in storms and filaments, in winds and waves, in flashes that span the galaxy. It bridges matter and energy, structure and emptiness. It connects the smallest charge in an atom to the largest arc across a nebula. We often view the universe as cold, empty, and distant, but electromagnetism offers a different picture, one of constant motion, interaction, and connectivity. Space is not silent. It hums with energy, pulses with rhythm, and carries the echoes of ancient events across incomprehensible distances. And perhaps as you lie beneath the sky, watching the stars that flicker gently above, you are not just seeing distant suns. You are looking into a field of energy that stretches around you, through you, and beyond you. A field that unites light and life, that links your own body's tiny sparks to the colossal electric arcs of galaxies. You are part of it, a brief flicker in a longer circuit, a single ripple in an infinite field. And while you may never hear the universe's electricity, it is always there, moving in silence, carrying the currents of everything. Chapter 10. The force that shapes everything and still hides in plain sight. It is easy to overlook electricity. In a world illuminated by screens and powered by countless machines, it has become familiar, too familiar. Flick a switch and the room glows. Plug in a device and it comes to life. Electricity seems so thoroughly domesticated that we forget what it truly is. Yet behind its convenience lies a force of staggering importance, one that quietly governs the structure of matter, the function of life, and the very appearance of the universe. Electromagnetism is not just a part of nature, it is one of its foundational pillars. Alongside gravity, the strong nuclear force, and the weak nuclear force, electromagnetism defines how the universe behaves. But unlike gravity, which pulls all mass toward mass, or the nuclear forces, which operate only at subatomic scales, electromagnetism acts at every scale where charge exists. Its reach is vast, its influence constant. At the level of atoms, it is electromagnetism that holds matter together. Electrons orbit atomic nuclei not because they are physically attached, but because they are drawn inward by the electromagnetic force. Opposite charges attract, and in the microscopic spaces of matter, this attraction is intense. But the balance is delicate. If electrons are too close, they are repelled by each other. If too far, the nucleus cannot hold them. The structure of every atom, and by extension every element, is determined by this equilibrium. The periodic table itself is a map of electromagnetic behavior. Each element's properties arise from the arrangement of its electrons, how tightly they are bound, how freely they move, how they interact with other atoms. Metallic bonds, covalent bonds, ionic bonds, these are not separate phenomena, but different expressions of electric force. Even the shape of molecules, from water's polar geometry to DNA's double helix, is guided by fields and charges. Electromagnetism also defines the surfaces of things. The sensation of touch, the resistance you feel when your hand presses against an object, is not a result of direct contact. Atoms never truly collide. What you feel is the repulsion of overlapping electron clouds. As you move your hand, electric forces prevent it from passing through matter. Solidity is not physical in the traditional sense. It is electromagnetic. You walk on floors, hold tools, and type on keys, not because matter is solid, but because charges resist each other across invisible boundaries. Light, too, is electromagnetic. Every beam, every color, every reflection is a wave of oscillating electric and magnetic fields. From the warmth of infrared to the penetrating energy of X-rays, the electromagnetic spectrum gives us sight, heat, radio, communication, and imaging. We perceive only a narrow slice, visible light, but the full spectrum spans from wavelengths longer than a planet to those shorter than an atom. What we see as color is the frequency of light, determined by how atoms absorb and emit energy. These emissions occur when electrons move between energy levels, releasing photons, particles of light. The brightness of a star, the shimmer of a soap bubble, the glow of a firefly, all are interactions between matter and electromagnetic radiation. The visible world is painted by invisible rules. In technology, electromagnetism provides the foundation for nearly everything we build. Motors convert electric current into rotational motion using magnetic fields. Microphones and speakers transform sound into current and back again. Antennas transmit signals by creating changing fields in space. Semiconductors control the movement of charge at microscopic scales, enabling computation, memory, and logic. The entire digital world exists because we have learned how to manipulate electric and magnetic fields with precision. Yet even the most advanced systems still follow the same fundamental laws that govern the orbit of electrons or the propagation of light. There is no separate physics for machines and matter. The behavior of circuits, the strength of magnets, the operation of lasers, all are described by the same field equations that govern the universe. In biology, this force sustains life itself. Neurons transmit signals as waves of depolarization, momentary shifts in voltage across membranes. The heart contracts in response to rhythmic pulses initiated by specialized pacemaker cells. Sensory systems, from vision to touch, translate electromagnetic interactions into perception. On a molecular level, enzymes interact with their targets through subtle electromagnetic patterns. Protein folding, cell signaling, even the assembly of complex structures inside a developing embryo, All are shaped by electrical gradients, charge distributions, and field effects. In astronomy, electromagnetic radiation is the messenger that brings the universe to us. Telescopes collect light across all frequencies: radio, infrared, visible, ultraviolet, X-ray, and gamma, each revealing different structures and processes in the cosmos. Stars emit light because of electromagnetic interactions in their cores and surfaces. Galaxies glow because charged particles spiral through magnetic fields. Even the faint afterglow of the Big Bang, the cosmic microwave background, is a relic of electromagnetic radiation released when the universe first became transparent to light. And still, for all its pervasiveness, electromagnetism remains unseen. The fields themselves are invisible. We do not see the electric tension between charges. We do not observe the magnetic lines curling around a current. We see only the consequences: the spark, the light, the motion. The force is always present, but rarely visible. It hides in plain sight, quietly enforcing the rules of structure and change. This invisibility once made the force mysterious. In the early days of its study, thinkers struggled to make sense of how something could reach across space, shaping the motion of objects without apparent connection. The concept of a field was revolutionary, a shift from the idea of forces acting at a distance to the idea that space itself could carry energy and influence. Today, we accept fields as foundational, but their invisible nature still creates a kind of conceptual distance. We rely on them, we model them, we simulate their behavior, yet we rarely visualize them as real. They are everywhere, and yet remain abstract. And perhaps this is why electromagnetism, despite being so essential, still feels elusive. It may help to imagine space not as empty, but as structured, not filled with particles, but shaped by potential. The electric field of a single charge extends infinitely, diminishing with distance but never vanishing entirely. That field interacts with others, combining, canceling, amplifying. The universe becomes a vast web of relationships, each point of charge altering the geometry of its surroundings. In this way, electromagnetism is not a force acting on matter. It is a property of matter, a feature of how particles are embedded in the fabric of space. The field is not separate from the particle. The two are inseparable. The behavior of matter cannot be described without reference to its field. This understanding leads naturally into the quantum realm, where electromagnetism becomes a force carried by particles, photons, and where fields fluctuate even in vacuum. At this level, what we think of as empty space teems with activity. Virtual particles pop in and out of existence, field values shift unpredictably, and uncertainty governs interactions. Even here, electromagnetism is at work, guiding the behavior of electrons, defining the stability of atoms, setting the rules of quantum chemistry. And yet, with all our knowledge, we still do not know why it is the way it is. Why does the electron carry exactly the charge it does? Why are positive and negative charges equal and opposite? Why is the strength of the electromagnetic force what it is, not stronger, not weaker? If it were different by even a small amount, the chemistry of life would not function. Molecules would not form. Stars would burn too quickly or not at all. The universe would be unrecognizable. In this sense, electromagnetism is not only a force, it is a condition for existence. It sets the stage for structure, for memory, for light, for life. And it does so quietly, patiently, without demand. We live inside this force, move through it, think with it, grow by it, rarely stopping to notice. And perhaps that is the most remarkable thing, that something so essential could remain so silent, that the force which shapes our every interaction, our every breath, our every thought, does not announce itself, but simply is. invisible, ubiquitous, fundamental. Maybe the universe is not made of objects, but of interactions. Not of things, but of relationships, ripples, fields, flows. And maybe we too are not separate from that, but expressions of it. We are patterns in motion, written in the language of electromagnetism, shaped by a force that hides not in darkness, but in plain sight. Everywhere, always, within and beyond. If you're still awake, my friend, you've just traveled through the quiet architecture of the universe, shaped by an invisible force that flows through your body, your thoughts, and the stars themselves. If your eyes are still open, there's another video waiting for you. But if they're heavy now, sleep well and sweet dreams among the stars.